Hello there, hello everybody, and welcome to this new open class, ROS Developers. Welcome everybody. So today we are going to have a very interesting class again. We are going to be working the first part of the class with a simulated robot, and then at the end we are going to change to a real robot. In this case we are going to be working with the BotBox, which is a very cool learning kit that we have prepared at the construct. And for this class we are going to focus on learning about odometry and more specifically about laser-based odometry. So yeah, I hope that you like this class, and let's get started. So as always, first of all, please let me know if everything is fine in terms of video, audio, if everything is working good, so that we can keep going. Then, meanwhile, I'm going to be opening here I'm going to be changing here to my computer scene. So let me do that right now. There we go. Okay. And let me go to the class page here so that I can see your comments and everything. Page here. All right, so I can see there Siyet says that everything is good. Also Henrique. All right, excellent. Then we are ready to get started, so let's go for it. Now, I don't know if you are new to these open classes, if you are already veterans. In any case, you have to know that the very first thing that we need to do before starting the class is to get the today's class project. Okay, every class, every open class that we are doing has a associated project or ROSJECT, how we call them. Okay, and this is crucial for everybody because it's going to allow you to basically actively participate in the class by practicing yourself, by testing yourself, everything that we are going to be doing during the class, all the programs, everything you are going to be able to replicate it yourself by using your ROSJECT, right? So yeah, Gilbert says that he's new, but I don't know if I trust you, Gilbert. Your name rings a bell, actually. Yeah. All right. So what to do in order to get today's class ROSJECT? Very easy. Just click on the button that appears here right above the chat, which says fork and open the class ROSJECT. Okay, I'm going to click here myself. There we go. And then this is going to redirect you, as you are going to see in a moment, to the main ROSJECT page. Okay, here you are going to have at the right side the streaming area with the live stream, the chat, so that you can post your questions, comments, feedback, whatever you want. In my case, I'm going to remove this, and so that I have some more space to show you everything that I'm going to be doing here, right? But in any case, I'm going to open it here because I still want to be able to read the chat and everything. Now, yeah, so first thing that's going to happen is that you are going to be redirected here to the main ROSJECT page. It might take some seconds to completely load the environment, so just be patient. But besides this, another thing that has happened is that a copy of today's class ROSJECT has been generated in your account. All right, you can see it here in the main page, but also if you go to the My ROSJECTs area here in the left menu, you are going to also see here the ROSJECT for today's class, and you are going to have this in your account forever. All right, so not just for today's class, but if you want to get into this ROSJECT tomorrow, next week, next month, you are going to be able to do it. All right. Okay, then let me go here to the open here the live class so that I have the chat. There we go, and let me go back here to my ROSJECT page. It should be finishing loading. Okay. So yeah, please, everybody, go ahead and click on the button in order to open today's class ROSJECT. Yeah. So in case that anybody has any problem with this, just let me know, and I will try to help you, but I want everybody to have his copy of today's project, okay? Very, very important, especially because this way you are going to be able to better follow the class. Yeah, because in the construct classes, we are not just talking and showing images, but actually we are testing live in robot simulations or even in real robot that we are going to be doing later today. Everything that we teach, that we do, we focus it on practice. Yeah. So with everything is done with practical examples. Okay, so here you can see how my ROSJECT environment has finished loading, and the first thing that I can see here is the notebook. All right, here is where all the information for today's class is going to appear, all the different theoretical explanations, images, graphs, code, commands to execute, everything, you have it here in the ROSJECT, okay? So if at any moment you get lost, you can come back here and get back on track. Okay. So yeah, I'm going to wait a few more seconds to make sure that everybody has his ROSJECT loaded. So have you been able to load the ROSJECTs there? Yes, no? Any issues? David Oleski says yes, also Henrique, also Shri Krishna. Okay, awesome. Then, today's class, laser-based odometry for ROS2. Then, first of all, in order to talk about laser-based odometry, we need to know or introduce what is odometry, right? So do you all know what is odometry? At least I'm pretty sure that most of you have already previously heard this word, right? Odometry. Very common concept in robotics, right? Yeah. So basically, in simple terms, the odometry refers to the process of estimating the position and orientation, yeah, position and orientation, also known as pose, of a robot over time from data sources, yeah. These data sources can be encoders, inertial sensors, or extrapolating from previous poses, or even from a LiDAR, right? Yeah. Then the most typical method, yeah, of getting odometry, the one that you are going to find in most of the robots is wheel encoders, yeah? So you get information from the wheels in order to process the odometry, yeah? Using a set of formulas, you can compute this from the wheels movement of the robot, right? For instance, if the motion of both wheels is at the same rate, in this case we are talking about a basic two-wheeled robot, okay? A differential drive robot, which is the most basic example. So, for instance, in this case, if the motion of both wheels is at the same rate, same speed, this means that the robot is moving forward or backward, right? In a linear direction. Now, if one of the wheels is moving and the other is stationary, this means that the robot is turning or rotating either clockwise or anti-clockwise. Okay? And if the wheels are running at two different rates, then the robot is moving on a curved path. Okay? So, with these very basic assumptions, or basic, so I mean, all these that you can see here is pretty obvious, yeah? So, applying mathematical equations for all of these, we can end up computing how much the robot has moved, yeah? So we can end up having the final position and orientation of the robot, which this, in our case, would be the odometry, right? Now, I mean, here there are many more things involved, but this is not the class for that. I don't want to get into too much theoretical details. So if you want to investigate a little bit more or learn a little bit more on this, I suggest you have a look at our basic kinematics of mobile robots course, okay? Here in this course, you are going to find much more in-depth explanations of all these, all the mathematical equations, and how to even program those mathematical equations into Python scripts in order to compute odometry, okay? But for that, if you want, you have this course to check it out. Now, why is odometry crucial or so important in the robotics world? Well, it's very important because it's used in many important systems or processes in robotics, such as mapping, yeah? Whenever we are mapping an area, for instance, mapping a warehouse, we are using odometry for localization also, yeah? So in order to know where a robot is placed on a map, also odometry is involved. For autonomous navigation, yeah, one of the most basic and important tools in robotics. So the ability for a robot to be able to autonomously navigate through an environment. Here we also have odometry involved. Also, we use odometry for feedback control, for instance, right? And many more things. So odometry is a crucial, a very important concept in robotics. Now, how to measure odometry? Yeah, so we know that odometry is very important in robotics. It is important for many different processes. But how do we get the odometry of a robot? How can we compute this? Well, so we already had a quick overview of one of the methods, which is using wheel encoders. Yeah, so wheel encoders measure the rotation of a robot's wheels to estimate its distance traveled and changes in orientation, right? This is one of the methods, probably I would say the most typical one, okay? Using wheel encoders, we can measure a robot's odometry. We can also use other sensors such as IMUs, inertial measurement units, yeah? Also, there are other methods which are known as visual odometry. So for that, we use cameras or depth sensors, you can think of a Kinect camera, in order to track visual features in the environment as the robot moves, okay? This is a very interesting method, and I'm going to make a spoiler, yeah? Because in today's class, we are going to be focusing on this method, laser odometry, okay? So how to compute odometry based on laser data, based on a laser sensor. This is the topic for today's class. But for the next week's class, we are going to be checking on this topic, visual odometry, right? So how to compute odometry using a camera in this case. So it's going to also be very interesting. So I am leaving this spoiler here, okay, about next week's class. Then there are other methods, such as GPS, for instance, or also very typical in robotics is to fuse the data of different sensors, right? So for instance, you can have wheel encoders, laser odometry, yeah? And then you can fuse both odometries in order to generate a more accurate, a more precise odometry reading, right? Because computing odometry with wheel encoders has some problems, as well as computing odometry with using just a laser data, yeah? But if we combine both, then we can produce a much more accurate odometry by fusing the data from different sensors, okay? Also very common method in robotics in order to get a more reliable odometry estimation, right? Now, for this class, for today, we are going to be focusing, as we have already said, on laser or LiDAR odometry. So why? Well, there are different scenarios. For instance, there are some cases where you are not going to have wheel encoders, right? So how to compute odometry? Well, if you don't have wheel encoders, but you have a laser data, you can compute this odometry using this LiDAR data. Yeah, and this is the case of the robot that we are going to be working with today, which is the BoxBot. Yeah, so we don't have wheel encoders. Therefore, what we are going to do is to use LiDAR data in order to generate this odometry. Another very important point is to get rid, let's say, or overcome the slippage problem. Yeah. What is this slippage problem? So imagine that you have wheel encoders in your robot, right? And these wheel encoders are going to track the odometry based on the robot's movement, right? But what happens, for instance, if the wheel is rotating, but the robot is not moving? For instance, if the wheel is slipping over the terrain, yeah? In that case, there is going to be an error, right? Because the encoder is going to think that the robot is moving because the wheel is moving, but actually the wheel is slipping over the terrain. So the robot is not really moving. And then an error is going to be introduced into the odometry. This is known as the slippage problem. Okay, so this can be overcome, for instance, using laser-based odometry. In LiDAR-based odometry, we don't have this problem, yeah, because we are computing odometry based on the laser data. So we don't care if the wheels are moving or not. Yeah. Also, to get rid of accumulated error. Yeah. So wheel odometry errors increase unboundedly as the distance traveled grows due to the compounding of small errors. Yeah. So with wheel encoders, usually you are going to be accumulating errors over time. Yeah. So for that, you can use laser-based odometry in order to correct these errors. Yeah. So these are some cases where LiDAR odometry or laser-based odometry can be very helpful in robotics. Yeah. So far, so good. Are we following? Yes, no? Any doubts, any questions so far? Marcus says no, but I think that was from a previous question. Right, Marcus? Henrique says yes. All fine. Okay. Okay. So we are getting close to the practical part, okay, where we are going to put all this on practice. But before that, one last concept to introduce. Yeah? Okay, so how is odometry computed based on a laser, right? Very well. So we know that we can compute odometry based on laser data, but how it is actually done, okay? So there are different algorithms. In this case, we are going to be using the ICP, or Iterative Closest Point algorithm, okay? This is probably the most commonly used to compute odometry based on laser data, okay? And it has some more complex things inside, but we are going to do I'm going to try to do a basic explanation to try to summarize how this ICP algorithm works. So basically, how this works is that the ICP algorithm is going to start by estimating an initial translation and rotation between two consecutive laser scans. Yeah. So imagine that we have the robot, and then we are going to have a laser data, right? And then we move a little bit the robot, and then the laser data is going to change, right? Then we are going to have two laser readings which are close but are not equal. Yeah. Then the ICP algorithm is going to compute a transform between these two laser readings. Yeah. So it's going to, you can think of it as it's going to create a relation between the two readings. Yeah. There are different methods for doing this, but in this case, if you want to get a bit of more detail, I'm going to share later an article that you can have a read through, okay? Now, it's going to compute an initial transformation between the two readings, yeah? And then, yeah, so the algorithm computes the transformation that best aligns the corresponding points in the two scans, in the two laser readings. Then, after computing this initial transformation, the algorithm is going to iterate to improve the alignment between the scans. Yeah, so it's going to repeat, it's going to do several iterations in order to improve this alignment, right? So at the end, we are going to have something like this. Yeah, so after several iterations, the algorithm converges on a much better alignment. Yeah, so the key geometric insight is that even with initial poor associations, so even if the initial transformation is not very accurate, right? Iteratively reassociating and reestimating the transformation drives the scans towards a consistent alignment. Yeah? So, summarizing, the ICP algorithm enables accurate odometry estimation by iteratively aligning consecutive laser scans to minimize the difference between them. Yeah? In simple terms, this is how the ICP algorithm works. Okay? Yeah? Now, in our particular case, yeah, because this is very fine, but this is all theory, okay? So we want some practice and some practical applications of all this. So for this, we are going to be using the ROS2 laser scan matcher package, okay? You have a link here in the notebook. Here you have it, yeah? So this is a ROS2 implementation by Alex Karavaev. Actually, the implementation is not made by him. What he has done is to port a ROS1 based package into ROS2. Yeah, but we are using this. We are going to use this ROS2 laser scan matcher package. Okay. Now inside here, what we have is an ICP implementation developed by Andrea Censi. Okay, and here I have linked an article which explains actually more in detail how this implementation works. Okay, so in case that you want to have a look at the mathematical theory behind all these ICP algorithm, you can have a look at this. Okay, but I don't want to get into all this. I prefer to actually get it tested in a real case, in a real robotics scenario. Right? So this is what we are going to do right now. All right, we are going to be using this ROS2 laser scan matcher package in order to compute odometry data for our robot here based only on laser data. Yeah? And for that, we are going to use this package. Why? Because it provides quite good performance. Yeah, it is quite simple. Yeah, so it's not a super complex program, but despite that, it's very robust. It's quite robust. Okay, we are going to see it in a moment that it works quite well, and also it's very easy to configure. Okay, so just by tweaking a few parameters, we can configure it very easily for different robots. Okay. In our case, the launch file that we are going to be using is this one, okay? So, at this point, let me already open the code editor so that we can see this file where it is, okay? So, in order to open the code editor, you have to go here to the bottom menu, yeah? And here, the second icon, which says code editor, you can click here, and this is going to open the graphical code editor, right? So here you can go inside the ROS2 workspace, SRC, And here you are going to find this ROS2 laser scan matcher package, okay? And inside here you are going to find the launch file, which is named start.matcher.launch.py. So if you double click, you are going to have the file here, yeah? So here we have the file. This is the file that we are using in order to launch the laser scan matcher program, yeah, which is this executable. If you are curious, you have it here also. Inside the SRC folder, you have the C++ program here. You can open it and check it out, right? This is the program that implements the ICP algorithm. So you can have a look here at the details of how this program is, it works in the insights, yeah? How it's implementing this ICP algorithm, okay? What we are doing just is to launch it, and what we have to worry about only is to fine-tune some very specific parameters. In this case, we have 5 parameters that we are going to be changing, right? First of all is the base frame. The base frame indicates what is the frame to use for the robot base, yeah? So this frame might change between one robot and another, yeah? Maybe for one robot is base link, for another robot is base footprint, for another robot is link chassis, okay? So depending on the robot, this might change. So you have to pay attention to this. Also, the odom frame. Which frame to use for the odometry, yeah? Here, we are setting the name odom matcher, yeah? So the odometry data is going to be published on this frame, odom matcher. We also need to provide the information of the laser frame. So the laser of the robot in which frame is publishing, right? This can also vary depending on the robot or the laser model. In our case, the frame in which the laser is publishing is LiDAR, okay? And finally, 2 more parameters. One is publish odom, where we just specify the name of the topic where we want to publish the computed odometry data, yeah? So our algorithm is going to compute odometry data based on the laser sensor, and then it needs to publish this information into a topic. So here we specify the name of this topic, odom matcher. And then finally, we specify whether we want to publish the transformation between base link and odometry or not. Okay, in this case, I am saying that yes, I want the program to compute and publish the transform between base link and odometry frame. Okay? Yeah, so as you can see, quite simple configuration, and in most cases, just by tuning these parameters, you are going to be able to adapt this code to any robot. Okay, so if you have a different robot, you can use the same package and just pay attention to these parameters. Okay? Now, you might be asking, hey Alberto, but how can I know for my robot what is the name of the frame for the laser? Okay, that's a good question. And I'm going to show it to you right now, how to do it, okay? Now, before anything, what we are going to do is to launch our simulation, okay? So it's time for practice, it's time for testing our program in a robot and see how it works, right? So for this, we are going to be launching this simulation of a BotBox here in a 7-11 environment, okay? And in order to start the simulation, we have to execute this command here. Okay, you have it here in the notebook in the launch the simulation section. So we are going to open a new terminal by clicking on the first icon that we have here in the bottom, which says web shell. Yeah, if you click here, this is going to open, as you can see, a new terminal. Okay, now here what I'm going to do is to basically copy the command from the notebook and paste it here into a terminal and then execute it. All right, and this command is going to start the simulation of the BotBox robot. Here we have it. Let me make it bigger. Okay. There we go. So in my case, as you can see, this is something that it can also happen to you. Okay. So pay attention. In my case, as you can see from the expected image, I don't have the robot. I have the environment, which is the 7-Eleven, but I don't have the robot. Okay. This happens sometimes the first time that you launch the simulation. Okay. But don't worry. If this happens to you also, if you have the robot in the simulation, no problem. If you don't have the robot, like it's my case, don't worry. All you have to do is to Control-C, so you stop the command here, okay? And then we have to close the simulation just by clicking here in the cross button at the top right corner. We click here in order to close the simulation, yeah? And then there is one more thing that we need to do, which is to, sorry, change. We need to manually stop the GC server process that it's running here, okay? So in order to find the GC server process, you can run this command. Let me share it here with you in the chat. Okay, so basically this command, what it does is to show a list of all the processes running, and then we are filtering the processes that contain the GZ characters. Yeah, and then now in order to kill it, we can run kill -9 and just the ID of the process, of the GC server process, which is 5736. Okay, so kill 5736. There you go. Now, if I repeat the command again, you can see that the process, the GC server process, has disappeared. Okay. Now, after this, if I relaunch again the command, same command to start the simulation, now it's going to load properly. Okay, or it should load properly now. Let's see. There we go. Okay, so now we have the simulation and we have the robot. You can see it here in the simulation as well. Okay. Yeah. To make sure that that your simulation is running, if you want, what you can do is to open a second terminal by pressing here in the create new terminal button. And in this second terminal, you can run ROS2 topic list, for instance. And then you should see the simulation topics, right? The scan topic, command belt topic, etc. Okay? And note that there is a topic here named Odom, okay? In a moment, I'm going to come back to this because it's very interesting. Yeah? So, has everybody launched the simulation? Yes? No? Any issues? Does everybody have the simulation running? Simulation running, no issues, says Henrique, also Marcus. Okay, excellent. Then, now it's time to run our program, right? So, in order to start our program, what we have to do is to execute the command that we have here to start our laser scan matcher program, right? So again, we can copy the command from the notebook and paste them directly here, right? Important, don't close the first terminal, okay? Here is where the simulation is running, so don't close it. If you close it or you stop it, then the simulation is going to die, okay? We don't want that. So I'm going to rename this terminal to make sure that I know that here I have the simulation running. And then in the second terminal, here I'm going to run the my program, okay? The launch file that we have just reviewed. There we go. Okay, excellent. So now I have my simulation running here and my laser scan matcher running here, okay? If you have some warnings here, don't worry, okay? You can ignore them. Then I'm going to open a third terminal here to analyze some things, okay? So let me put here, here I have the scan matcher, okay? So now here I'm going to run a ROS2 topic list command, right? And then here I can see the Odom matcher topic, right? So this topic is the one that my program is publishing. Remember that I set this name for the topic? Now, as you can see here, I have another topic which is Odom, right? So we know that this Odom matcher is generated by our program, right? So this Odom matcher topic is the odometry computed from the laser data. But does somebody know what this Odom topic is? Anybody has a guess of what this is? Somebody wants to guess? Enrique says, from Gazebo. Very well, Enrique. Exactly. Nick says, produced from the wheels. Not quite, no. So the answer is from Gazebo, okay? This odometry is being generated by Gazebo, by the simulation, okay? So basically this means that this is a perfect odometry, yeah? This odometry is computed directly by the simulator, so it's going to be perfect, yeah? Because the simulator always knows where the robot is, yeah? To be more precise, this odometry is being published by a plugin, by a Gazebo plugin, okay? By the differential drive plugin. In fact, okay, we can have a look at this. Odom by ROS2 topic echo once Odom. Okay, so let's have a look at what do we have in this odometry information. If we scroll down to the position, we can see that the value of the position is 2.44 meters in the x-axis and minus 0.92 in the y-axis. Okay? So these values correspond to where the robot has been spawned in Gazebo. Right? Yeah? So if I go to the launch file, where I am spawning my robot, which is in here, Tortoisebot Gazebo launch, I'm going to see that the coordinates are these ones, 2.44 minus 0.88, okay? There's a bit of error in the y-axis, but basically it's this, yeah? 2.44 and minus 0.93. Yeah, these are the values where I have spawned my robot. Yeah, and this odometry is generated by Gazebo. Yeah, then what is going to be the value of the other, which is Odom matcher? Let's have a look. So my other Odom matcher says that the values are 0 and 0, okay? This is a 0. This is basically a negative exponential, so it's the same as 0, yeah? So for my Odom matcher, the positions in x, y axis are 0, 0, which makes sense, right? Because wherever I start my algorithm, that is going to be the 0, 0 position, yeah? Right? Yeah, do you understand the difference? Here, this is important. Yes, says Nick. Okay. Okay, now, let's do some testing, right? First of all, we can have a look at the odometry by launching RVs. Here you can test this, but I want to skip directly to the real test, which is by moving the robot and checking the values here, yeah? So I'm going to move the robot using the keyboard teleop, yeah? You have the command here in order to launch the keyboard teleop program, yeah? So I'm going to copy it from here. Then I'm going to open another terminal here to launch the keyboard teleop. And this is going to allow me to move the robot, right? So I want to do one thing, okay? Let me create here a text file to grab some notes. Odom readings.txt, okay? So I'm going to use this as a notes for checking the values and comparing them, yeah? So basically I want to check how good is my odometry based on the laser, yeah? And for that, what I can do is to compare it with the gazebo odometry, right? So let's do this test, which I think is going to be very interesting. Then, initially, let me get the values of the odom topic, yeah? So the odom topic shows me that initially these are the values. Let me copy it from here and write it here, right? This is initially, and the odom matcher is basically 0, 0, right? We can approximate it to 0, 0x and 0y, right? Okay, now let's move a little bit the robot by using the keyboard teleop. So let me put this here, move this here. Actually, let me put the simulation here in the right side and this here. Okay, so let me move a little bit the robot here using the keyboard teleop. Let me move it forward a little bit, okay? Let's go forward a bit. So there. Okay. I don't know, till the entrance of the 7-Eleven, for instance. Okay. Let me move it a bit more. And I'm going to stop here. For instance, even I can move maybe a bit more. Okay, there we go. Okay, so now let's check again the odometry readings. Let's start by the gazebo odometry. Okay, so the new values for the gazebo odometry are, let me copy them and paste them here. The new values are same more or less in the x-axis, yeah, so same in the x-axis, and in the y-axis it has changed more or less 0.8, right? Yeah, 0.8 more or less, right? Why in the y-axis? Well, now I'm going to make this question after I check the odom matcher values. So let me check now the odom matcher values. Let's see what we have. Okay, so for the odom matcher we have this x and this y, right? So x is 0.75 and y is 0. So what can we notice here? One thing that we can see very clearly is that in the odom matcher, the change in position is in the x-axis, while in the gazebo odometry, the change in position is in the y-axis. The x-axis remains the same, right? Does somebody know why this happens? Any guess? Do you think it's an error? Is my program wrong? Different frames. Yes. Yes. So The gazebo odometry basically is computed based on the world frame, right? This is why I have this initial position, right? Which is based on where I am spawning the robot in the gazebo world. Yeah. If you remember, I am spawning the robot here. But not only this, you can see here that I am providing a rotation to the robot. Yeah. So I am spawning it with a certain yaw, right? So because of this, when I am moving the robot forward, with respect to the gazebo world frame, this is the y-axis. Yeah, because of this rotation, right? This is why for the gazebo odometry, the change is in the y-axis. While for my odom matcher, the reference frame is the robot, basically. It's base link. Yeah? The reference frame for my scan matcher is base link. It's the robot itself. So since I am moving my robot forward, obviously the odometry is going to change in the linear x. Yeah? And now comparing the two values, we can see that they are more or less, with some error, they are similar. Yeah? So around 0.8. Okay? Now we can try also, if you want, to rotate a little bit, for instance, and see how this affects. Yeah, so we can try, for instance, to rotate to the left here and move a little bit the robot towards the entrance. Let's do that. Right? So I'm going to move towards the entrance. And now, if everything is working fine, right, I should see some change in the y-axis in my odom matcher, right? So if I check again the odom matcher, now I can see that it has changed also a little bit here in the y-axis. Yeah. So we can see that more or less, right, the odometry resulting from the laser data is quite accurate, right? Yeah. Doing this simple test, we can see that it's working pretty well. Okay. Now I want to test it also in the real robot. Okay. So this is what we are going to do right now. Very well. So in the simulation, this is working quite good. But what about the real robot? So this is what I want to actually see. Then let me do this. So let me stop everything here. We are not going to be working more with the simulation. So you can stop everything here. Well, actually, not in your case. Sorry. Because the real robot test, I'm the only one that I'm going to be able to do it, okay? For obvious reasons, we cannot connect all at the same time to a robot. So this I'm going to be doing it myself, okay? Then here I'm going to be closing the simulation, and then I'm going to connect to the real environment, to a real BoxBot, okay? There we go. I'm establishing the connection. Should be almost done. There we go. Connected. So now I can see here the robot has appeared in the environment, right? So let me have a quick look, first of all, to make sure that my robot is connected. We can see Ricardo also over there, right? So I'm going to open a terminal and run a ROS2 topic list, first of all, to make sure that I am connected to the robot. Okay, so here I can see the topics of the real robot, actually, right? Then, before running the program, I want to make sure of something. So, do I need to change something from the simulation to a real robot? So, earlier at the class, I was mentioning about this launch file, yeah? Then, these are the frames that we should be worried about. Then, in general terms, if the simulation is well done, it's going to be using the same frames as the real robot, okay? But this is not the case always, okay? So I always recommend that you check this. How you can check it? For instance, a very simple way to do it is to run the following command. ROS2 run tf2 tools view frames. Okay, this is going to generate a tf3 of the robot, and we are going to be able to see all the different frame names and how they are connected. Okay, this generates a PDF file, as you can see here, that you can download and visualize very easily. See? So this is the frame tree of my robot. Then I can see that I have a base link very well. The Odom frame, I don't have it, which is expected. Yeah, because this one I'm going to generate it with my program. Then the laser frame here is LiDAR. And in my real robot, I can see that the frame is also LiDAR. So we are good. Then finally, the topic where I want to publish the odometry, this is, it doesn't matter, so you can put whatever you want here. And then also I want to publish the TF from base link to an odometry frame that I'm going to be adding to this tree. Yeah, and this frame is going to be named Odomatcher, right? Okay, so in this case, we can see that the frames are equivalent, so we don't have to make any change. Well, actually, we have to do one change, right? Because in simulation, we use what we, a parameter, which is use sim time. Yeah, this is a very well-known parameter in ROS, that when working with simulation, we set it to true. But when working with real robot, we have to set it to false. Yeah, because we are no longer working with a simulation, so we are not going to be using the simulation time. So we have to set this to false. Just this important step that you always have to take in mind when moving from simulation to real robot. Okay, so we are ready to go. Let's compile our package just to make sure that we take this last change. Then here I'm going to source, and I'm going to be launching my odometry again. So ROS2 launch, ROS2 laser scan matcher, and start matcher launch by. There we go. Okay, so my program is running. Let me open a second terminal just to make sure that I have the topic, ROS2 topic list. Okay, so here I have my frame, Odomatcher. Let's have a look at what value do we have here. So ROS2 topic echo once Odom matcher. Okay. Let me put here at another reading. So real robot. And then here we have 0, 0. Expected, right? So we were saying some minutes ago that wherever we start our scan matcher, that is going to be the 0, 0 position, right? So this is expected. We have just started our program, right? So the initial position is 0, 0. Now, what we are going to do is to move the robot, the real robot, forward and see if the odometry is accurate, okay? So Ricardo is there, and as you can see, he has there a meter with exactly 1 meter. Yeah? So this, what is pointing right now, Ricardo, that is exactly 1 meter. So I'm going to move the robot forward until the end and see what is the computed odometry, right? So let me do this right now, just by launching the teleop keyboard to control the robot here very easily. So let me put this here. And now I'm going to reduce a little bit the speed to make sure that I don't break anything in the rear robot. And let me start moving forward. There we go. Wait, I'm moving too fast. Let me reduce a little bit the speed. There we go. And there I stop. Okay, there I stop. All right, so now, more or less, the distance should be 1 meter, more or less, right? So let's stop the teleop and run and check again the odometry reading. Okay, and we see exactly 1 meter point 04. 05. Ah. Okay, yeah. So Ricardo is telling me that it's actually a bit more because I didn't stop the robot in time. But the reading that we are getting from our program is 1.05. Okay. Yeah, it moved a couple of centimeters also in the other axis. So these are the readings that we have. 1.05 in the x-axis and 0.02 in the y-axis. Okay, so we can see that right now the odometry is quite accurate, right? So what I'm going to try now is to rotate the robot a little bit also and see how that affects the program, right? So I'm going to, because moving forward is always the easiest scenario, right? But what if I start rotating and turning and so on? So let me rotate a little bit to the right. Here. Okay. Let me. So, okay. Let me. One second. One second. There it goes, there it goes. My rotation, my robot is getting a bit crazy. Yeah, I don't know why it's not responding correctly to the keyboards. Yeah, I don't know why it's not responding. Oh, now it's working. Okay, now it's working. There was some kind of delay, but now it's working. Okay, so shall I move forward, Ricardo? Yeah, okay. So let me go ahead and move forward. Stop. Okay. Okay. So let's see. So right now I have put the algorithm to the limit because of all the rotations and everything I have made. Okay. So let me get a reading. I don't know because I have been rotating the robot a lot. But actually it's quite good. It's 64 centimeters to the y-axis. Yeah, I think we should do something because we can try. Let me try. Can we try to repeat the experiment? Because I lost my keyboard tele was not working for a moment. I don't know why. And now it's working properly, so I can repeat. Okay. Okay. Yeah. Okay, so we are going to set up the everything again. I'm going to restart actually also the scan matcher. because for a moment I lost control over the keyboard teleop. It was not responding. So I want to test it in a more controlled environment. Let's try. Yeah, okay. Ricardo says we are good to go. So let's move forward. I'm going to reduce the speed more now. Well, actually, before this, let me get the first reading, which... okay, the initial position is not... Let me... There we go. Okay, now we have it. So we have zeros at the starting position, right? There we go. And then now let's start over. Let me run the teleop. Now, yes. Reduce speed and start moving forward. Okay, there we go. Okay. Stop. I have moved a little bit to the... Yeah. Okay, so let's see what we get. We have moved a little bit to the right. We are aware of that. Don't worry, Ricardo. But we can see that, yeah, so it's pretty accurate. We can see that the distance in the x-axis is actually 1.00 meters, and there are 6 centimeters here in the y-axis, which makes sense, I would say. Okay, then let's... Okay. 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 Okay, okay. Okay, so now let's do the rotation to the... yeah, let's rotate to the right. There we go. Shall I move there? Okay, not yet. Ricardo, maybe you can move that panel just a bit so that we have more space to move forward. Yeah, okay. So I'm going to move. Okay, stop. Okay, we have collided a little bit with the meter. Okay, let's see what we have. Okay, and the reading is, yeah, almost 1 meter in the y-axis now. Yeah, so we have some displacement in the x-axis, some more, which makes sense because we have moved a little bit on that direction, and 1 meter more or less in the y-axis. Yeah, so Ricardo confirms that more or less. Okay, yeah, more or less. We have some error of some centimeters, but it is expected. All right, so yeah, I think that we can conclude that the experiment was successful. And yeah, so relying only on the laser for getting accurate odometry data is not probably the best advice. The best thing would be to combine this laser-based odometry with other sources. For instance, wheel encoders, camera odometry, which is what we are going to be seeing in the next class, right? Yeah, just to correct these small errors that can appear, all right? So, so yeah, basically that's all for today's class. I want to finish by saying that this setup that we have here, including the warehouse with the BoxBot robots and everything, you can get it in our kit, which is the BotBox Warehouse Lab. So this is a kit that we sell, everything already packaged, for you to create a warehouse environment anywhere. You can do it in your home if you want. You can do it in a university for teaching. So you are going to get all the environment with the floor, the panels, everything. 3 tortoise bots like this one with grippers, with cubes to grip. So you can create a full warehouse environment for testing navigation, perception, manipulation, many things. Yeah. And here you have a link in order to have a look and check out this BotBox Warehouse Lab. I encourage you to give it a look because it's super interesting. Okay, and as you can see, it can be used to learn or to teach many robotics related concepts. In this case, it's odometry, but you can also teach manipulation, from manipulation to perception to autonomous navigation, etc. All right. So for the attendance of this class, okay, we have provided here at the very end of the notebook a coupon for 500 euros discount. Okay, this coupon is going to be valid until the end of April, of this April. Yeah, so by using this coupon on the following link here, you are going to get a 500 euros discount on the warehouse, on the BotBox Warehouse Lab kit. Okay? Yes, so super interesting opportunity. I really encourage you to give it a look. And yeah, so for what the class is, I'm going to leave it already here. I hope that you have enjoyed the class. Let me have a look here at the last messages. Great package, says Marcus. I say goodbye till next open class. Have to go as well. Thank you for the class. See you next week. Thanks. I have to go. Thanks for another great open class. Can't wait for the next week. Okay. So yeah, thanks a lot as always for all of you for being here today with me during the class. Next week we are going to be working again on the BotBox Warehouse Lab, but in this case we are going to be testing camera-based, or also known as visual odometry. Okay, so another super interesting class. I hope to see you all there. And yeah, so from my side, I'm going to leave it here. See you in the next one. And until then, as always, keep pushing your ROS learning. Bye-bye.